can get about 2 to 4 times more energy per sea area from wave power than you get from wind power. So which do you want?
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about the pursuit of a solution for wave energy. I've covered wave or tidal powered only one other time, way back in episode 17. I thought we'd see full-scale wave energy farms by now. Unfortunately, most technologies are constricted to wave pools where they're still being tested. My guest believes they're close to breaking out into the open water with a full-scale wave farm. Like many guests who've had success, they've settled on a simple, robust, and affordable design. So why does wave energy have so much trouble? My guest says the ocean can be pretty unforgiving. Waves are 800 times heavier than air. They can tear up the wrong equipment. You also have to set these units out in the open ocean, where maintenance is tricky. He says many wave power designs are simply too heavy, too complicated, or both. Many wave power designs don't make very much energy. Also, he claims wave energy doesn't get the same tax breaks or subsidies as wind or solar. This results in a high levelized cost of energy that makes wave power less attractive than other renewable energy options. My guest says they hope to get considerable power from their units, between 500 kilowatts and 2 megawatts per module. Strung together, he says wave power can have more energy density than an offshore wind turbine. We also discuss how wind and wave can be great companions. I visited an offshore wind facility back in episode 118. You could potentially locate my guest's wave units in between giant wind turbines. He says wave energy can be produced even when the wind isn't blowing, increasing the power capacity at the same site. My guest hopes to have a commercial facility in place in the next few years. With a robust design philosophy and potential partnerships with technologies like wind, wave energy could form a fine flotilla for our energy needs. My guest today is Jan Schuldheimer, founder and CEO of NoviOcean, a Swedish wave energy developer. Jan began developing his wave converter back in 2011. They've had successful demonstrations out in the open ocean. Their current unit is about the size of a kayak, but NoviOcean hopes to have units the length of yachts churning out megawatts of energy sooner rather than later. I hope you enjoy my conversation with Jan Schuldheimer. We're here with Jan Schuldheimer, founder and CEO of NoviOcean. And Jan, it's been 5 years since I've had a wave energy guest. I think most of us can agree that we expected to see more commercial deployment to this point. So help us set the stage. Why has wave or tidal energy been so hard to commercialize to this point?
Well, first of all, very happy to be with you and to talk to your listeners. It's a valid question. Many have tried for many years. Many have failed. And also, most likely, many will fail in the future because the oceans are rough. And we've all been out there, I think, either boating or swimming and felt the enormous forces out there. Water is 800 times more heavy than air. So at the same speed, the forces are enormous. That's why you have the huge wind power towers. But for the much less area, you can have the same energy coming out of the waves, which I guess many have thought about and felt, well, there are all these waves coming in. Why don't anyone use that? So the reason is basically it's a rough environment and many have broken down. Technical reasons is just the forces are so enormous. Waves can be up to 30 meters high. And of course, then they're going up and down quite quickly. Both the vertical way and also on the surge is quite huge. The other thing is the economical side. Of course, if you want to be in the business of energy, you can have subsidies for so long. While wind power and solar had subsidies on a large scale for many years, that made them grow larger. Wave power tidal has some subsidies, not so much. We'll be getting there. So I guess we can all agree that wave power has the potential to create lots of energy, but it has to both survive and also be economical. And on the economical side, many have been too heavy. If you go to a shop somewhere, you want to make something, the first question will be, what is the weight? And then the guy will give you the price back because it's normally a strict correlation between the weight of something and the cost. And many out there have, for instance, a weight of 100 tons in the water, and they create perhaps 3 to 6 to 7 kilowatt. You can drive a moped on that, and it's as heavy as 70 cars, and it's complex. Far out to sea. It doesn't make sense, does it? So we have to get down to the weight. For that weight, you should be making an average of 200 kilowatt. Then it does make sense. And then it comes in also to the mechanical things. If you have, for instance, gearboxes, in our case, our system lifts 600 tons in a 4-meter waves, 10,000 times per day. If you have wires going around the wheel, or you have accumulators, or you have cogwheels, metal to metal, it's very hard to have it last for a long time. In our case, we use water to metal in a hydropower plant, then it lasts for 40 years. So it's all these things coming together. And then also the energy out, the shape of the buoy, where it's connected. We'll get back to that later on. But it's basically technical and economical. Both has to function well.
Certainly. You point out on the website that the challenge comes down to power delivery, density, and weight. It also mentions that many of these technologies have a lot of complex moving parts. You just alluded to that. How do you simplify your process and still make it tough enough? I think that's the key, making it tough out there in that environment to handle whatever the ocean throws at it.
Our system, then, if you're going back to what we have, is like a large 38-meter surfboard times 8 meters times 4 meters. And it floats 0.7 meters down, so that the horizontal forces are much less. When we're lifting, in the lifting phase of the wave, we may be down to 3.5 meters, but then you get out of the wave again, and you have a less horizontal force as the way to both get a huge power of energy and then also to survive. And then also on the way it functions, many systems have a round buoy, for instance, and many are floating free out in the water. In our opinion, you have to have the difference in power between 2 points. So in our case, it's tightened to the seafloor. Then you have the lifting force from the wave. And that difference in height and power is where you extract the power. So if you're free floating out there, and if you are using the wrong laws of nature, it might be more difficult. And also, if you have many complex moving parts, it's also expensive. It's like an old Volkswagen Beetle was a bit cheaper to run than today's Formula One car. So it's the same thing. You can make everything more complex, more heavy, more parts, but it's better then because costly and something breaks down. So in our opinion, it has to have a huge lifting force, and it has to have few parts, light parts, and well-proven parts. And as a consequence of all that, then you have a high power output to a low cost. And many are in the opposite direction. You have to satisfy those requirements to be able to also have the economic numbers in your side.
Yeah. Getting more into the technology, help me understand this. You have what we think is a turbine on top, hydraulic cylinder beneath the water, and the upward and downward motion of the waves is activating the system. Is that roughly what's going on? Oh, here we go.
Yes,
This is why it's
no, I'm showing Jay here on the video camera. You can see it, unfortunately, with the other listeners, but it looks like a yellow submarine, actually, which people call it. It's a large rectangular float, and it's, as mentioned, then 38 times 8 times 4 meters. And on that one, there is a so-called power take-up connected, and that is a long cylinder, about 1 meter in diameter, can take up to 80 bars of pressure. And then there's a tube on the side of the cylinder going upwards. And when the wave is lifting, we get compression in the lower end of the cylinder, and water is pumped upwards. And on top, you have your all standard hydropower plant. It's up in every mountainous country around the world. So we're taking that one, put it on the float, and the water pressure then comes at the same pressure and speed in a hydropower plant. For instance, 50 bars of pressure hits the Pelton turbine, just 1 meter diameter, and then spins a generator around on the same axle, generates electricity. There's a cable going into land for the connection, same as with floating wind, for instance, or floating solar. So it's very simple. It's just a hydropower plant out to sea, 3 parts, a float, a cylinder, and a turbine. Also essential, as I mentioned in the beginning, it's water to metal, and that lasts for a much longer time than metal to metal. And then also for the hydraulic cylinder, imagine driving your car at the highway, and then you are doing 60 miles per hour, and you hit the brakes with 50 kilos, and you stop that heavy car in 20 meters. And the next time you try pulling the handbrake, doing the same thing. That's the difference between using a hydraulic cylinder versus mechanical cogwheels. So we will claim that for this 600 tons, you have to use hydraulic cylinder. And then to extract that power over time, so it lasts, you have to use water to metal on the Pelton turbine. It's very simple in our mind.
Well, that was very helpful with the demonstration. And since we're recording video as well, I'm glad we turned our cameras on. The unit in your videos looks about the size of a kayak. You said you can build it up to 500 kilowatts. And give us those dimensions again. So it'd be bigger than what we're seeing in the demonstration videos, I take it, yeah?
Yes, the one you see in the videos on our homepage, that is the so-called prototype. We're running for 5 months offshore, and also a wave tank in France and in the UK. Now, the big one will be 38 meters long, as mentioned, and 8 meters wide and 4 meters high. high, like just a rather large barge, you may say. That's for the 500 kilowatt unit. Sometimes the rated power doesn't say so much. Many in the sector talk only about rated power, but that doesn't pay the bill, does it? It's what you produce on average per year, which produces the power. That's called the capacity factor in energy. In our system, then, out on the coastline of, for instance, California, Oregon, Spain, France, Portugal, you produce about 250 kilowatt on average. Some more outside Norway or Ireland, or, well, also north part of Oregon, you have more waves then. Same goes for then the west coast of South America, North and South Africa, Indonesia, New Zealand, Australia, Japan, many areas around there. We can later go to 2 megawatt, still with 50% capacity factor, but this is a good size to start on the pilot system. The average power output is then much more than anyone else out there, as far as we know.
Sure. So you said it could go up to 2 megawatts for a single unit. That's quite substantial. Would there be any physical limit to how much you could get out of it, or do you get to a point where it's just too big?
Perfect question. It has to do with nature, actually, the wavelength. Because in the summer, when there's a little bit lower waves, the distance between the waves can be down to 30 meters, and in the winter it's a bit more. And it can also be up to 200 meters sometimes. If you're driving a large boat in small waves, you don't feel them, because you're cutting the waves. So if you go beyond a certain size, you will be cutting the waves in the summer. Of course, in locations like I mentioned, outside Ireland or in Norway, where you have higher waves, you could go even larger, because the summer waves are 50 meters or larger, perhaps, in distance. So we're saying then, if you go with a float about 60 meters times 11 meters, then you can take out 2 megawatt. But that's about the most. But the essence is also how much ocean do you need? You can get about 2 to 4 times more energy per sea area from wave power than you get from wind power. So which do you want? If you are a country giving permissions out to sea there, you won't have energy coming into the shoreline. And the fishermen want their sea area, and the shipping lines want their areas. So if you can get away with more power per sea area, it's much more beneficial for all parties. The stability of energy is of essence. Nowadays, when you have sun in California, you might even have negative spot prices. Other times at nighttime, or when there is no wind or no sun, you might be paying, at least in Europe, you can pay up to 50 cents per kilowatt hour. And that's because there's a lack of energy right then, and you have to buy expensive fossils. So wind is gone for 10 days a month. Sun is gone for half the day. Add those together, you have 40% of the hours of the month basically without wind or sun power. At that time, we're burning fossils to the most. But in more fossils now in 2015 than we have in the Paris Agreement. It goes the wrong way. But if some system are able to take those 40% out, the most important hours, and then you guessed it, wave power is the solution. And why could that be? First comes the sun up in the morning, and the sun creates heat more unevenly over land and water. And that heat creates wind. And the wind over time and distance creates waves. And waves are the biggest battery on Earth. When the wind goes down for a couple of days, doesn't matter. Waves are still coming. Those 40% of the hours when we're burning the most fossils to the highest cost, then you have wave power. So the value of those megawatt hours are so much higher, both for the environment and for the customer.
Jan, let's talk a little bit more about how the ocean works. So you touched on this about the intermittency and how reliable wave energy is. You said the capacity factor was about 50% in California, for instance. So what is going on there? When are the waves not producing power? We know what happens with solar, with wind. It's a little bit more seasonal, I believe. Are there long spans of time where you are not producing wave energy? How does that work?
Your listeners can go into our homepage, look at the Documents tab, and you can see graphs showing how intermittent wind is, and then you can see how stable wave power is. Wave power is much more stable. On the Pacific coastline or on the Atlantic coastline, you basically always have waves, and you can power basically 24/7 for the whole month. It goes up and down, but the base load of wind power offshore, for instance, is very often down to 10-15%. You have 100% could be on an area, we have 100 megawatt, and then in non-winter days, you are down to 10-15 megawatt. If you have the same size area of wave power, you will hardly get below 30%. So it's much better for the environment. But if you combine wind power and wave power, they're offset of time. Then the base load will be between 40-50%. So we have solved the equation basically for the system, because the combination for the utility owners is so much better than going to buy gas somewhere. So instead you can go green by using wave power instead of buying more fossils.
So in the Pacific and the Atlantic, you say you pretty much have waves all the time. Why wouldn't you have 100% there? Is it because you're generating more power with more intense waves?
Yes, it's the same like with both wind and sun. Sometimes you have more. In our case, we produce 500 kilowatt in the 4-meter waves, but the waves, let's say in Oregon, the average could be 1.8 meter, San Francisco perhaps 1.67 meters. So if you add this on an annual basis, we can make 250 kilowatt, 50% capacity factor is kind of standard locations, and then you have some more in the more northerly locations and a bit less in the southerly. And it's like this, well, the world spins around anti-clockwise and the wind's the same direction. So there's a bit more on the west coast, and also in the center between 20 degrees north, 20 degrees south, the waves are lower but longer. So if you're going outside Nicaragua, for instance, then the waves are less but they're longer. So in that case, we can keep the same power takeoff system, just have a larger float. The float could be then 80 times 50 meters, and you still have 2 megawatt coming out then if you're going for that size. Or for the 500 kilowatt, increase from 38 to perhaps 50 meters and 10 meters wide, and you still have the same capacity factor, which is very difficult then for most other systems. They cannot change just a part like that. But the float is cheap to build. It just can be built in a shipyard. I want to see this out in the thousands in the coming decades. So we will be offering license production. Any larger competent shipyard can build between 50 to 70% of this system themselves, take care of their own region and take care of their own market, own competence enhancement with the local people working there, and just build it, get it out there. In that way, we can have many, many more units out there than we can by ourselves. We also want to work with partners, large oil and gas companies. So if you are Shell, BP, Total, or Exxon, listen in. Or if you are ENGIE, EDF, EDP, we do have what you are looking for, what your customers look for, because they want to have clean energy at the right times, at the right cost.
One more question about wave energy, because with wind energy, the phenomenon is you can't have one wind turbine directly in front of the other one. The wind is being disturbed by the blades. How far apart do you need to have your collectors in front of another unit? Does your unit absorb some of that wave energy and diminish it?
It's actually a question. Same with wind power. You are killing something behind it. It's called blanking, and it's relevant. In the beginning, you can have less sea area for the same energy by wave power than wind power. So the blanking is so much less. Why? Look at the rotor size. They are huge. So we have a large blanking behind that rotor, and also wind is less dense, of course. So in our case, we are doing some research on that. We'll be talking like 150 meters in between them, and then lay in 2 lines. So we have 2 rows, you may say, but then positioned in between each other. So we have an opening there. But then again, if you are in California, where they have the shoreline erosion, then you will see, if you put them tight together, what happens then? Well, they diminish the shoreline erosion because you're killing 30% of the waves behind. So we can do both at the same time. And also, in California, where you have sunny locations, or any place where you have sun, we can add 750 square meters of solar panels on top, because we have the float anywhere out to sea, and we have the cabling, have the systems. So that's a 120 kilowatt system on board as well. We can have a hybrid, because if you have floating solar, which is now popular in some places, then the cost for the structure and the cable is 75%. Panels are cheap. Well, we have the structure, we have the cable. Why not use it? So for California, we can offer you both wave energy, which is more stable than wind. We can offer you more sun power, and we can offer you shoreline erosion. How's that for a deal?
Jan, the reason I was asking about that is energy density, right? You want to pack these things together as much as you can when you site them. Also, one of the things I talked about when I did an offshore wind episode was the transmission aspect of it. Bringing that back to shore would have to be a big part of the cost. And one of the things that you had in your website was you have a good levelized cost of energy. Does that include the transmission to take it back to shore? Because that would be maybe unique to your technology. There's nothing usually else out there in the ocean that needs a power line.
The advantage, again, with wave power versus wind is that wind power is normally out to sea 50 kilometers for 2 reasons. Because they're visually obstructive and they're noisy, and the winds are higher out there. But the waves, they continue for full power in towards the shoreline, especially if it's a straight shoreline. And it's just when the depth becomes more shallow that the waves are less efficient. Most wave power wants to be at depths deeper than 40 meters. If you get to less depth than that, the waves might be breaking. And that's not good for anyone to be in. But that 40 meters comes normally from 500 meters from the coastline to perhaps max 5 kilometers. So the cable will be between 1 to 10% the length of what you have for wind power offshore, which is a huge cost saving, of course. And then also you have all the OPEX, the maintenance, the transportation forth and back, go up about 50 kilometers, 30 miles. It takes a long time for most boats, and you need a much larger boat as well. That's why we have lower costs regarding the question about the LCOE. The OPEX, the maintenance can be, and also of course the cable, shorter cable. And usually the same thing as with wind power, you have a substation to collect all the power, and using first a dynamic cable to take the movement up and down in the waves to be connected. Then you gather them together in a substation, which then have a converter to have the right frequency and voltage. And you could also do the amps depending on the large or small grid.
So one of the things I'm thinking of is, are you talking to offshore wind developers to more or less piggyback on their transmission system? That was the one thing that we talked a lot about with Dominion Energy and their project they have off the coast of Virginia, was the transmission wheeling it back to the shore. Would you be able to build a farm of your NoviOcean units and use that system, since it's going to be out there in the ocean anyway? That might be a good way to maybe have some synergy, right?
Very good question. Yes, you can definitely use the same cable. If there is a kind of location where you have good waves, not perhaps in the North Sea because it's by the UK, but if you have a straight coastline like California or Oregon, definitely. Since we use different sea area in some way, the wave power units do not disturb the wind, or opposite, it doesn't matter. So we can be in between the wind towers because they are 1 kilometer apart. There has been some investigations or suggestions about having them in front because you can kill the waves, which is good for the wind power towers, especially also with a floating wind, which I think is relevant for the US West Coast because of the depth. So it can be definitely collocated, or you can connect on the same cable further in towards land and use that one. It could be combined in one area close to land and one out there by the sea, definitely. So, and you have, of course, then have the same maintenance personnel going out anyway. So if they are climbing up in that wind power mast of 150 meters, they can also look into the wave power at the same time.
Right. I would much rather do maintenance on your units than go up a wind tower. I'm a little bit afraid of heights. So Jan, wrapping up, the next step is to build your 38-meter commercial. When do you think that's going to happen? And what do you think your timeline is to being fully commercial?
Given the climate crisis, I would like to be ready yesterday, but it takes time and costs money. Right now, we have grants of about 3 million from Sweden and the European Union. And the total cost, if it add also the PV panels for the first full-scale pilot, will be costing in the range of 7 to 9 million. We are open to discussions with venture caps and also utility companies, oil companies, because we have what they need. And the more money, the faster it goes. So with that kind of money, we'll be in the water in 3 years. Then you have testing and certification for 1 year. Then you have a pre-commercial area. But if someone really sees that we have a problem with the environment, understands the 40% I just mentioned before, what that can give both for the climate and also for the bottom line of any company going with us, then double the money. We'll do it in 2 years. So, and of course, someone will do that with us and take the glory and be part of an enthusiastic team, have a good time and do something really great. Or many will sit on the sidelines, but the ones on the sidelines will be there most likely forever, because we have room only for 1 or 2 large partners from the utilities, oil company sectors, and they will have the name on the side saying, for instance, company XXX Renewables in 35 meters times 3 meters. And it's very cheap compared to what our competitors have been using, 10 times more for half the power output, by the way.
Well, good luck to you on that. And we certainly hope to see these on the water soon. Jan, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
It's the best of the fossils, and it's quick, and it can regulate the power up and down quickly. So it is needed for quite some time. But still fossils, and then wave power is better.
Crude oil.
More dirty, heavy to transport, still needed to some extent. And of course, they will keep drilling for crude oil as long as there is less green energy.
Nuclear.
It's interesting. In Sweden and in Germany, for instance, there was a long history of people being against nuclear for obvious reasons. Nowadays, it's popular again because it's more green than the other ones. I think it will be coming back, but the timeline is actually too long to make they need the impact in short time for our environment.
Coal, and I'll add coal with carbon capture.
Well, the carbon capture they're doing, the filters are better than they used to be. Carbon capture is coming online. It seems it still has many, many years to go before they can capture carbon from free air at a large amount without burning more energy just for that. But unfortunately now coal is produced more and more in Germany just because they lost the gas from Russia. We want to fight all these fossils by doing what we do best, wave energy.
Wind.
Well, it's out there. They are now big because they got subsidies. In our opinion, wave power should get the same. Wind power is to stay, and the combination of wind power and wave power has a base load, as I mentioned in the beginning, 40 to 50% instead of 10%.
Solar.
Of course needed. It's cheaper and cheaper and cheaper. The panels are made sometimes on a less sustainable way, perhaps in China on coal for transportation, but definitely it's here to stay. It's a good energy source.
Biofuels.
I think it's fine if you can use waste, for instance, if that's what is burned. But if you want to use land area, it just takes basically too much land.
Hydroelectric, and I think this is where we'll add you guys.
Well, that's what we have, don't we? Yeah. We just have it out on the water instead of up in the mountains. Of course, the ones running, no doubt, they are very efficient. Making new ones makes a large impact on nature.
Geothermal.
I think it's a good one. I think it's still kind of expensive, but I think it's on the rise. It's stable.
Energy storage.
That's the one I like, because people think batteries are the solution. It isn't. If you want to run Europe on batteries and solar and wind, I think you need like 12 billion EV car batteries. It just won't be possible or sustainable at large scale.
Energy efficiency.
It's always important to be efficient. With all the systems out there producing energy, of course, the more bang for the buck, the better, both when it comes to economy and also the emissions. All the green ones are definitely necessary. The batteries, in my opinion, is still questionable when it comes to the recycling and reuse. But green energy in general, with high efficiency, is what we need.
And then finally, fusion power.
Yes, I would be happy if they succeed. It's been in work, I think, for the last 30 years, more or less. I haven't seen any large gains on that so far, but if it works, if it's safe, by all means.
All right, Jan Schuldhammer, NoviOcean, thank you so much for your time.
Well, happy to be with you. It's been great. And let me, if I may, end with a quote from Larry Fink, BlackRock CEO. He said, decarbonizing of the global economy is going to create the greatest investment opportunity of our lifetime. It also leave behind the companies that don't adapt. Thank you.
Very good. Thank you, Jan. That was Jan Schuldhammer, founder and CEO of NoviOcean, a wave energy developer based in Sweden. I want to thank Jan for his time, as well as Auntie Santiago at Legendary Podcast for setting this up. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram at HostEnergy and Twitter at HostEnergyCast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 152. Be sure to join us next week when we explore the untapped potential of precious metal mining here at home. Until then, I'm Jay Dowenhauer. We'll see you next time.